We're still in chapter 29, still in the chapter where we started introducing magnetism. And now we're going to discuss this cool name, cyclotron motion. If you tell somebody that, it sounds very impressive, right? Cyclotron motion. But everything is reasonably simple, right? So what we're going to do now, basically we introduced fundamental equation which allows us to find magnetic force acting on a point charge. If your point charge exposed to the magnetic field, of course it is going to experience magnetic force, right? And we introduced that formula. So now we know that part of the foundation, and now let's try to apply it. Maybe we can find something interesting, right? And let's look at these two situations. Right, so you know that solenoid we discussed allows us to create uniform magnetic field inside, right? So that's how we can create uniform magnetic field. And so now let's imagine that you have for example, a proton, and you want to shoot it along the axis of the solenoid, through the center of the solenoid, for example, right? So what will be the force acting on this proton, for example? We discussed that actually yesterday, right, as part of the conceptual questions, right? Since in that case, velocity that way, magnetic field either this way or that way, but in both situations, magnetic field will be either parallel or anti-parallel to the velocity. In both cases, dot product of those two vectors give you 0, because the angle is either 0 or 180 degrees. Both cases are going to give you 0 magnetic force. As a result, in this case, that proton is going to fly along that straight line forever and ever without changing its direction and without changing its speed. So it's a boring motion, right? Pretty much nothing interesting, just a motion along a straight line. What can be more boring than that, right? It's like driving on a highway, right? And so, of course, we can call it, we can give it a fancy name. It's a uniform translational motion. Uniform translational motion. Uniform means that the speed is the same. Speed is basically magnitude of the velocity. So this situation, if you shoot the particle along magnetic field lines, you're going to see pretty much nothing. It's just a boring uniform translational motion. So let's make the situation more complicated. What if we turn the solenoid like this, drill the hole? And what if we shoot now electron perpendicular to the magnetic field lines? In this case, of course, there will be not 0 magnetic force. There will be some value of the magnetic force, and of course, if there is a force, of course, our particle is no longer going to move along a straight line, or is not going to move maybe with constant speed. So that force, of course, is going to change something in the motion of our proton, for example, right? So let's look closer, deeper in the situation when you shoot the particle perpendicular to the magnetic field lines. So that's what we have to do now. Okay, let me remove them from the field of view of the camera. All right, where's my flipper? Here it is. All right. So let's, again, as I said, look at the cases when when the velocity of the particle, charged particle, is perpendicular to the magnetic field lines. And again, with an attempt to see which trajectory are we going to get. Which trajectory we are going to get, right? So let's assume this situation. We have uniform magnetic field, maybe created by this gigantic solenoid, right? B is into the page, bunch of courses. Then let's shoot a particle, positively charged particle for simplicity. Let's say this is our proton, for example, and let's say it flies that way. So that is its velocity. And now, as I said, let's try to understand first conceptually which trajectory we're going to get, and then we will try to describe this trajectory, right? So In order to realize which trajectory we are going to get, of course, we need to understand, we need to get all possible information about the force, because force is going to change, is going to sort of create that trajectory. Because if you, for example, turn off this magnetic field, of course, magnetic force will be zero, and of course, this particle will just fly straight forever and ever, uniform translational motion. But since we have magnetic field, of course, there will be magnetic force, and of course, as a result, this particle is not going to move along a straight line. So there will be some kind of more complicated trajectory. So let's find everything that we can find about the magnetic force, and then try to deduce the trajectory, get some information about the trajectory. So fundamental formula, fundamental equation, which we just introduced yesterday and practiced today. Force acting on the charge. It's a Q and cross product and V of V and B, right? So let's first find the direction. 1.5 steps. But since charge is positive, so it's basically one step. Direction of V cross B gives us direction of the force. So V cross B. V is, okay, let me stand it like this. So V is that way, right? So I have to align my hand along V, and then B is into the board. So it means that I need to orient my hand like this, so that I can bend my fingers into the board. Right, you see, I'm bending my fingers into the board. And as a result, my outstretched thumb gives me the correct direction of the force on this, acting on this particle. So it will be that way. And again, you remember, force in this case is all the time is perpendicular to both of these vectors, velocity vector and magnetic field vector, right? Okay, so magnetic force acts this way. Now, next, whenever you have a force acting on the object, it leads to what? According to Newton's second law, it leads to acceleration. Whenever there is a force, there must be an acceleration. Acceleration describes what? Acceleration describes changes in the velocity. So it means that if there is a force, there must be some changes in the velocity. So there must be some influence of this force on that velocity. So what does this force change in our velocity? Does this force change magnitude of this velocity? It's perpendicular to the velocity, right? Force acts perpendicular to the velocity. Of course, naturally, it cannot change magnitude. It cannot change speed of this particle. So it means that with this force acting perpendicular to the velocity, the speed of this particle is going to be the same, right? So again, speed, it's a magnitude of the velocity. So it means that our particle is going to move with exactly the same speed all the time, because this force cannot change magnitude. Okay, so it means that our motion is going to be uniform. Again, you remember, what does it mean, uniform motion? It means that your object moves with a constant speed. Again, magnitude of the velocity. Okay, so this force cannot change magnitude of the velocity. But then what can it change? Velocity, it's a vector, right? It has a direction and magnitude. So force cannot change magnitude. So, but then there is still a direction of the velocity. And this force changes direction of that velocity all the time, because this force perpendicular to this velocity. So this, what can this force do? It can change direction of this velocity. So basically, it just keeps yanking this velocity, changing its direction all the time. Right? Let me demonstrate in something. Let's say I need to stand probably like this. Yeah. So let's say this is my velocity vector, this pinky marker, and this black marker, this is my force, right? So, and now let's try to follow this particle. And again, you remember, so this force can change only direction of this velocity, right? So first, particle tries to, of course, let's say over a short period of time dt, of course, particle tries to move straight because it has inertia. Of course, particle tries to move straight, but because there is this force, of course, this force is going to change its direction. So particle moves a little bit, and changes its direction. And immediately, this force adjusts its direction and it will be perpendicular. Because look, according to the fundamental law, which is just above me, right, or behind me, right? So force is perpendicular to the velocity all the time. The God created nature this way, right? I don't know. So all the time, magnetic force is perpendicular to velocity, right? You see, perpendicular to the velocity. So it doesn't matter what's the direction of the velocity, magnetic force is going to be perpendicular. So in our case, magnetic force changes its direction of the velocity, and immediately adjusts its own direction to be perpendicular still, all the time, non-stop. Magnetic force changes direction of the velocity and also adjusts its own direction to be perpendicular all the time to the direction of the velocity. So let's try to follow the particle. So it tries to move straight, but force changes its direction. Then again, next delta t again, velocity tries to, object tries to move straight, but the magnetic force changes its direction. Then again, next, then again, next, then again, again. And okay, now I need to change my position. So, and it will keep doing this, right? So you see, which trajectory are we going to get? Circle. It's a circular motion. Cyclotron motion is just the circular motion of a charged particle which moves perpendicular to the magnetic field. Right? So just now we just discussed conceptually, right, justifying that trajectory is going to be circular. Right? So this magnetic force changes or can change only direction of this velocity, right, giving us circular motion. Have you seen something like this in Physics 1? Actually, multiple times. The most probably memorable example, satellite motion. Motion of a satellite around the Earth. Every time we assume it's a circular motion, right? Yeah, there are orbits which are circular, right? But of course, in the case of a satellite, which force provided this circular motion? Force of gravity. But now it's a magnetic force provides this circular motion, right? Or another example, if you have a cord attached to some, I need to color those tennis balls so that they will have different color. All right, some rope attached to the, for example, this ball, and if you start spinning it with that rope, right? Again, you're going to get circular motion of the ball, and which force provides the circular motion? Tension of the cord, right? And who remembers? What's the name of an acceleration? So this force, you remember, any force provides all the time an acceleration, right? In this case, this force, which acceleration is going to be produced by this force? What's the name of that acceleration? Centripetal acceleration. Centripetal acceleration, right? And so as a result, we have this circular motion, right? And of course, whenever there is a circular motion, you remember from Physics 1, there must be centripetal acceleration. Or if somebody tells you, okay, I have a trajectory with, I don't know, 5 meters per square second centripetal acceleration. So if you hear that there is a centripetal acceleration, you should immediately deduce, okay, so that person has circular motion. Because circular motion and centripetal acceleration, they're inseparable, right? Sort of, it's this force acts like, you know what, people, I know, cowboys, they train their horses, right? So there's a rope attached to the horse, right? And the horse wants to run along a straight line, and they just keep yanking the horse. Okay, stay in the circle, stay in the circle. So that's what this magnetic force does. Just keeps reminding this particle, okay, stay in the circle, right? You're not going to fly straight. I will keep you moving along this circle. Okay, so that's a conceptual description. Of course, I can add, for example, what if a particle, for example, at this point, velocity still tangential, right, to this circle, but the force all the time adjusts its direction to make sure that it's perpendicular to the velocity. God created nature this way all the time. Magnetic force is perpendicular to the direction of the velocity. Or, for example, if the particle is over here, right? So again, still force is towards the center, giving us centripetal acceleration, right? Okay, so now, after this conceptual discussion, right, I think I convinced you in this circular motion. Now let's actually describe this circular motion. Let's derive maybe some equations, right? And what does it mean describing this circular motion? If you know the radius of a circle, right, you know pretty much everything about that circle, right? So pretty much for us to describe this trajectory, we just need to calculate or derive the formula which can be used to find radius of this cyclotron orbit. Yeah, actually, this is called cyclotron orbit, cyclotron motion. It sounds cool, but it's so simple, right? But sounds really, really cool, cyclotron motion. Okay, so now let's actually derive the formula for the cyclotron radius, right? Basically, in the fancy words, we can say again, we just want to describe this trajectory, this circular motion. And you remember, I already bugged you a couple of times in this semester. Which universal law can be used to describe any motion of any classical system in the universe? Everyone knows that, right? Newton's second law. That's basically the role of Newton's second law. It's an equation of motion which can be used to describe motion of any classical system in the universe. No restrictions. It's a universal law. It's like this magnetic force, Newton's second law, Gauss's law, Ampere's law. Those are universal laws which we basically take as an axiom, right, in physics. We just believe in them, right? Like in a cult, right? So, welcome to the cult, guys, right? So, we're believers. But actually, yeah, pretty much in every part of physics, right, there are some fundamental equations which we just basically, in which we basically believe. And why do we believe in them? Because they describe what we see around us. Okay, anyway, back to the description. Exactly the same picture. Let me just reproduce it. So the same magnetic field lines, particle travels this way, but now I change direction, change the color, right? Of course, circular motion. And so now our goal is just to find this radius of this cyclotron motion. Right, cyclotron radius, sometimes it's called, right? And as I told you, whenever we want to describe motion, we need to use Newton's second law. And we're going to use Newton's second law. And since this motion, it's not a motion along a straight line. It's a two-dimensional motion. The particle moves along a circle. Circle, it's a two-dimensional object. Of course, usually we use like x and y axis to describe two-dimensional motion. But now, since we have this circular motion, if you remember in physics 1, we used special coordinates. At least we use special names for those coordinates. They're still mutually perpendicular to each other. Okay, the first axis, t, it's a tangential direction. Okay, tangential to the circle, right? Instead of, for example, x, we use t, right? But of course, if you hate t, you can use t-lex. It's not a big deal, right? And then radial direction. So you see, mutually perpendicular. So instead of x and y, very often people use these axes, right? And they use them, they call them r and t. Again, radial direction and tangential direction. Okay, so let's apply Newton's second law along these two directions, like we did, like you did in physics 1, describing, for example, projectile motion of some ball flying in the gravitational field. So the same here. Let's apply Newton's second law in both directions. But of course, we need to see what happens with the force in terms of these coordinates. So force is still towards the center, right? Magnetic force. It's purely in the r direction. Right? And let's write the magnitude of this force. So force, we see the direction. It's in the positive r direction, right? So now we just need to know the magnitude. So absolute value of q v cross b. Q, absolute value of v, absolute value of b, and then of course sine of angle between v and b. But angle between v and b is 90 degrees. V is that way. Magnetic field is into the board, so the angle between them is 90 degrees. angle between them is 90 degrees. Right? So that's why sine of 90 degrees is 1. So as a result, we're getting just QVB. Right? Students like this formula. They remember QVB all the time, right? Okay, so that's the information about the force. And now, as I said, let's apply Newton's second law in both directions. First, t direction. And of course, there's no force, any force in the t direction, in the tangential direction, because the force, there's only one, and it's in the radial direction. So force in tangential direction is 0. And so now let's apply F equals ma, force equals 0, ma, it's m times acceleration in the tangential direction. So as a result, we're getting that acceleration in the tangential direction is 0. It means that we have a constant speed of this particle is constant. That's what we discussed in the previous slide conceptually, right? So now we're getting that from the Newton's second law, basically, right? So speed of the particle is going to be constant. So as this particle moves around the circle, it moves with a constant speed. Of course, I'm not saying constant velocity, because velocity is the vector. Speed, it's the absolute value of the velocity, right? So I can say, yeah, constant speed, but I cannot say constant velocity. No way, because direction of this velocity changes all the time, right? So speed is constant. So it means that we're going to have uniform motion. And of course, since we know it is circular motion, we can say that it is going to experience uniform circular motion. So now, radial direction. So F equals ma, but now, of course, acceleration is with the subscript r. And we already recall the name of this acceleration. It's a centripetal acceleration, right? So let's use that formula for centripetal acceleration. Usually students at this point, they forget about the expression for the centripetal acceleration. It's a v squared over r. R is the radius, right? So v squared over r. That's the formula which can be used to find the centripetal acceleration. And left-hand side force we just found, QVB, because now we are in the r direction, and the force is in the positive r direction, right? QVB. So now let's just write it down explicitly. So QV times B equals mass times centripetal acceleration. That's what we have here. So one velocity over here and over there can be cancelled. We need to find what? You remember, we need to find the cyclotron radius. These are psych, right? So we just need to solve for r, and as a result, we're getting, so it will be mv divided by q and times the magnetic strength of the magnetic field. Of course, it's in the denominator. So this is the formula for the cyclotron radius, the radius of the cyclotron orbit, right? We're going to use it occasionally. In plasma physics, it is used a lot, right? People who work with plasma, right? It's there. One of the favorite formulas, right? And guys, if I give, for example, a problem about this on the exam, I don't expect just use this formula, right? Every time I expect you grab Newton's second law, Lorentz force, magnetic force, and centripetal acceleration, and with this couple of lines, write cyclotron radius. Usually I don't give this formula in the formula sheet because it's not something fundamental, right? If you don't use it, I know, every day or maybe once in a week, you're going to forget it, because it's okay, because it's not it's not something fundamental. It's application of if you apply Newton's second law, Lorentz force and centripetal acceleration, yeah, you can get that easily. So every time I expect from students to get this formula and then only apply it to find cyclotron radius. Okay, so now we can describe this motion, trajectory of this motion. Now, next question. So if you let this particle move, right, for some time, of course, it is going to just keep circling. It will keep circling, right? First circle, second, and so on. So this is a periodic motion, right? And whenever you have a periodic motion, of course, your brain will start asking, so what about the period? And period is just basically time. Time it takes, a particle takes to complete one circle. Again, the period is just the time. It has units of seconds, right? It's the time to complete one circle. So If this motion is periodic, of course, next logical question, what about the period of this motion? Right? So, period of the cyclotron motion. At this point, usually if I ask a question like this on the exam, especially if students don't come to classes, they start panicking. They write bunch of nonsense, right? Because for them, whenever they hear word period, it's something complicated, right? But in this case, it's trivial, basically. If you don't see why is it trivial, I will guide you. And the key word why this question is trivial, the key word is uniform motion. You see, it's a uniform circular motion. But again, the key word is uniform. You remember what does it mean, uniform? It means the object moves with constant speed. If you still don't see how can we find the period, okay, let me guide you with a few additional steps. All right. Because after that, yeah, you will realize it's really, really trivial. Okay, let's imagine the simplest possible situation. Some distance, right? We know the length, for example. And let's say some bug crawls along this, distance, right? With constant speed. Very important. This bug travels with constant speed. And let's say I ask you, how can we find the travel time of this bug? It's a really insulting question, right? For anyone who is in this class, come on, it's stupid, silly. Okay, not stupid, but so simple, right? Insultingly simple. Of course, you take the distance and divide it by the speed. And that's how you get the travel time. But now, let's make it slightly more complicated. So what if I slightly bend this ruler and ask you the same question, and we have the same condition? We know the distance the bug travels, and we still know that this bug travels with exactly the same speed. And if I ask you the same question, what's the travel time? It's still insultingly simple, right? So again, it's just take the distance and divide it by the speed. And if I bend it more and I ask you exactly the same question, then of course the answer will be exactly the same. Take the total distance and divide it by the speed, because the bug travels with the constant speed, uniform motion. And if I keep bending, I'm not going to, I like this rule, I don't want to break it. All right. So of course, sooner or later, you will be able to bend that ruler into the circle. And if I ask you the same question with the same condition, we know the distance. Now it's just a circumference. And if we know that bug travels with the constant speed, in our case, it's a particle travels with constant speed. So how can we find time to complete one circle? Now everyone should be able to answer. You just take the circumference and divide it by the speed. And again, it's only possible because we have uniform motion. Speed is constant. So now everyone should be able to write. So period, which is the time to complete one circle, equals circumference, which is 2 pi r we just found, right? Cyclotron radius, and divided by the speed of this particle. All right. So you see, if you realize that, the question is simple, right? Actually, simple. Yeah, I don't want to say trivial, but very simple. But of course, if students don't come to classes, right? So very often they just they have no idea what they think. You need to apply some fancy special formula. No, it's a high school stuff, or maybe middle school. I don't know where you guys learn this. But anyway, so t, of course, now we usually the symbol for the period is t capital. T of cyclotron motion equals 2 pi r cyclotron divided by the speed of the particle, right? And cyclotron radius expression we just derived, so we just need to plug it here. Right? So we will get 2 pi v I put in the bracket, and here it's just my r cyclotron, mv divided by qb. And you see what happens with the velocity? It gets brutally cancelled. V in the denominator, v is in the numerator, so of course v gets cancelled, and we're getting 2 pi m. M, of course, mass of the particle divided by the charge times the magnetic field strength. And what first seems like a surprising result. Velocity disappeared from the period. It's at the very beginning, it's not obvious that velocity is going to just vanish. So how come? Look, guys, let's assume that we have here uniform magnetic field, right? And here's my particle, barely visible, right? So my particle entering this magnetic, or flying through this magnetic field. So since it travels perpendicular to the magnetic field lines, of course, it's going to experience circular motion, right? So if it travels fast, look at the formula, velocity is large, then cyclotron radius is going to be large. So if particle travels with large speed, of course, it is going to travel with over the circle with large radius, right? And let's say it gives you, let's say it takes 5 seconds to complete the circle. So larger speed, larger travel distance, right? So let's say time is 5 seconds. But if your particle travels with a small speed, smaller cyclotron radius, smaller cyclotron radius, right? Of course, smaller travel distance, smaller velocity, smaller travel distance, and its still ratio gives us exactly the same. For example, 5 seconds. So larger speed, larger distance the object has to cover, right? Larger cyclotron radius. Smaller speed, smaller cyclotron radius, and smaller distance it has to cover. But their ratio all the time is going to be the same, right? So it's going to give us exactly the same travel time for larger circle or smaller circle, because here it travels with larger speed, here with smaller speed. So speed is not involved in calculations of the cyclotron period of the cyclotron motion. And then of course you can ask, what about the frequency? Frequency is just a reciprocal of the period, so you just need to flip this formula. So frequency, of course, will be 1 over t, it's a qb over 2 pi m, right? Yeah, and that's what is important about this. That the cyclotron frequency and the cyclotron period does not depend on the speed of the particle. Great, so that's what cyclotron motion is, right? But it sounds so cool. Now let's look at the amazing consequences, phenomena, right? So let's look at a general situation. What if we just discussed what will happen if you send a particle perpendicular to the magnetic field lines? Basically, if you send the particle this way, relative to the position of the solenoid. We also know behavior of the particle if you send it parallel to the magnetic field lines. So now we know the situations. If you send parallel to the magnetic field lines, you're going to see uniform translational motion. Particle will just move straight. But if you send it perpendicular to the magnetic field lines, it is going to experience cyclotron motion, circles. Right. So now let's superimpose these two motions. So what if we have these magnetic field lines, for example, uniform magnetic field, right? And what if we send the particle at the angle to these magnetic field lines? Velocity neither parallel nor perpendicular to these magnetic field lines. So how can we describe this trajectory now? Now it's simple. If we decompose this velocity into two components, perpendicular and parallel to the magnetic field lines, like this, right? So let's say this is V perpendicular to the magnetic field lines, and parallel to the magnetic field lines. And we know what is this velocity V parallel. We know what is this V going to give us, and we also know the outcome of that velocity V perpendicular. So this V parallel is going to give us a uniform translational motion along the magnetic field lines, and V perpendicular is going to give us a cyclotron motion, circular motion around these magnetic field lines. So now we just need to superimpose these two motions. Again, translational motion along the magnetic field lines and circular motion, cyclotron motion around the magnetic field lines. So if you superimpose these two motions, what are you going to get? Circular displacement, circular motion, displacement, circular motion, displacement. I'm just superimposing two motions, uniform translational and uniform circular. We're going to get helical motion. So in this case, If a particle travels at an arbitrary angle to the magnetic field lines, we're going to get this motion, helical motion, right? V parallel gives us uniform translational, V perpendicular, uniform circular cyclotron motion. And now, if we understand this, now we can come up with we can describe amazingly beautiful phenomena that some of people saw. I haven't seen in my life yet, right? So maybe at some point I will, right? Okay, I don't want to pronounce that word, so let me guide you to that. Next slide. The sun, this happy face, right? So, but in reality, of course, it's quite a dangerous object, right? There are lots of complicated reactions inside of the sun, right? And as a result, the sun spits out gazillion number of high energy particles in all possible directions. Right? I know high energy electrons, protons, right? Some neutrinos, some. It's a lots of particles, and they have very they have very high energy, right? And that those particles, right, are called okay, solar wind. It's basically they create the solar wind, what is called. You've heard probably about this term, solar wind. It's just basically high energy particles produced by the sun, and they travel in all possible directions. And of course, some of them travels towards the Earth. And if you, for example, position here a human body, right, some human, right, that person will live maybe for, I don't know exactly, but for a very short period of time will live, because these high energy particles are going to interact with the molecules of our body and damaging them, and the body will just, yeah, the person will die very soon, right? So they're very dangerous, right, because of their high energy. And so, of course, these dangerous particles travel to the Earth, planning to kill us, basically, all. But nevertheless, we're still alive, right? Why? Because of the magnetic field. Because the Earth has this reasonably strong magnetic field here. Remember, we discussed it. So what happens? So when these particles start approaching the Earth, and you see magnetic field lines are bent like this, right? So they will start feeling these magnetic field lines, and based on the discussion which we just discussed in the previous slide, of course, they start circling. They start experiencing helical motion, and they start spiraling around these magnetic field lines, following the magnetic field lines. They basically guide it now towards the pole, these particles, poles, right? So spiraling around magnetic field lines, right? And so first, when they start feeling these magnetic field lines, the atmosphere of the Earth is still quite below, right? So not many molecules of air is over here. But when once they start approaching poles, once they start approaching the this way, let me stand it this way. So once they start approaching the poles, right? So they're getting closer and closer to the Earth. So they enter atmosphere, and of course these high energy particles start colliding with the molecules of air. Nitrogen, oxygen, right? So whatever we have in our air, right? So they collide, these high energy particles. Of course, what happens there? It's a quantum mechanics now, right? So after the collision, of course, these molecules get excited. They go to a higher energy level, right? And then during the de-excitation, they go to the ground level. Right. And when they go to the lower energy level, during this process, they will produce a photon. It's a quantum mechanics. At some point, you will discuss that, right? So, but anyway, after each collision, pretty much almost every molecule of air is going to produce a photon. I don't know, maybe oxygen will, I'm just making it up, maybe oxygen will produce a red photon of the red light. I know nitrogen will maybe blue or something else, or maybe green, right? But anyway, they will produce a light, small pieces of light, right? And so, do we see those photons? Of course, you realize I'm talking about the northern lights, aurora. So pretty much that's the nature of northern lights, these high energy particles from the sun traveling towards the Earth, wanting to kill us. but because of the Earth magnetic field, so these magnetic field lines are guided towards poles, right? And they start colliding with molecules, right, giving us this beautiful phenomena, aurora, right? Okay, let me open a few pictures, right? So yeah, of course, it's amazingly beautiful, especially this with the long exposure, right? And of course, now usually students ask after this absolutely logical question. Let me hold you for a couple of minutes. All right, ask me a logical question. So, does it mean that it's dangerous to live on poles? Because it looks like all these high energy particles travels towards the poles, right? Intending to hurt us there, right? But actually, it's not. Because there is another phenomena which you will learn probably in higher level courses of electromagnetism. So when these particles start moving towards the poles, of course the magnetic field there gets stronger, right? You see, density of lines is larger, so magnetic field is getting stronger. So as a result, these particles, they circle around the magnetic field lines faster and faster and faster and faster. And at a certain point, what happens, sort of like a mirror effect. Again, it can be described in physics. We're not going to get there because it's more complicated. So what happens basically at a certain speed, those charged particles, they stop moving in this direction for a moment. They stop for a moment, and then they start spiraling in the opposite direction, start traveling, for example, from the North Pole to the South Pole. Again, experiencing collisions with those molecules, right, of air. And of course, as a result, with each collision, they're losing their energy, right? So, and because of this spiraling along the magnetic field lines and collisions with molecules, they lose their energy significantly, right? And sooner or later, of course, they will lose their energy level, get to the level which is harmless for us, right? And as a result, above the Earth, there is a high concentration of high and not so high energy particles, right, which is called Van Allen radiation belt, right? And I'm just basically, before I was just trying to make a point. So these high energy particles, they cannot actually reach the poles because of this mirror effect. They actually they bounce back and start circling in the opposite direction, right? And maybe after one cycle or maybe two cycles between the poles, they will lose their energy completely, or the energy will be on a very low level, which is not dangerous for us. But anyway, so the point is, it is as safe to be at the North Pole as at any other point on the surface of the Earth, right? And so, yeah, the origin of this Van Allen radiation belt is just all these particles, high energy particles, which come from the sun. And of course, during the space travel, so it's one of the biggest issues. So we need to people has to pass through this radiation belt. So you need to protect people properly, right? So that they wouldn't interact with those high energy particles, which are going to give you lots of troubles, right? And pretty much none of the people is going to survive if you just expose somebody to those high energy particles. And now the second application, the cyclotron motion. The cyclotron. Basically, it's the first principle of work of the first accelerator. Accelerator is just basically a device which allows us to increase speed of charged particles. So how does it work here? So you see this gray cylinder? It's a permanent magnet, which creates uniform magnetic field. You see the blue vectors, magnetic field lines. Then on top of this permanent magnet, there is sort of like a tube spiraling out from the center, right? You see this. Of course, properly designed, calculated radius is properly calculated, and so on. Then there is a gap. So basically, that tube is divided into two parts. So to create a gap, and then AC power supply is attached to these two parts, right? So that we can create, for example, charged one side positively, the other side negatively, or the vice versa, right? So this side is negatively charged, that side is positively charged. Again, this structure, right? Okay, then at the center there is a source of protons. A source of protons just basically produced a proton, and of course, first it is produced. A proton is produced with a reasonably small speed, which is not enough. For us. We want to accelerate. We want to get the larger speed of those protons. So, all right. So once proton is produced, so it flies with very small velocity or speed, small speed, right? So as a result, small speed, v. Of course, cyclotron radius is going to be small. So it will, and you see, because it travels perpendicular to the magnetic field line, it is going to travel over a circle with small radius. So of course, we need to calculate properly and match that radius with the radius of our tube over which these particles are guided. So, all right, so it will travel along this small circle, right? And after half a circle, the proton will enter this gap, right, which is created between these two parts. So it enters the gap, and we need to calculate everything properly so that at the moment when proton enters this gap, we turn on the power supply, IC power supply, in such a way so that in front of the proton, that part is negatively charged. Behind is positively charged, so that the proton will be pushed forward, right? So it will be accelerated. It will gain additional speed over this gap which we created. So now when it passes this gap, of course, now it has larger velocity. Okay, larger speed. So larger speed, larger radius. So our tube must have larger radius. So that proton will still be inside of the tube. So now the proton follows this part of the tube, right, with the larger radius. And of course, after half a circle, it will enter the gap one more time, but in the opposite direction. So by that time, again, we need to calculate properly, design everything properly. So by that time, when electron enters the gap, now, again, it should see negatively charged object in front and positively charged object behind, again, so that will be accelerated. So by that time, polarity of this AC power supply must be flipped. So now this side should be negatively charged, and this side should be positively charged, right? So now again, it gets accelerated, all right, and now it will have larger radius. And now, of course, the radius of the tube must match that radius. So again, electron will travel along this tube. Okay, not electron, proton, sorry. Proton will follow along that part of the tube. And of course, after half a cycle, it enters gap again. By that time, again, we need to flip a polarity so that proton sees negatively charged object in front and positively charged object behind. Again, it will get accelerated and so on. So it will keep circling in these tubes, right, gaining more and more speed, right? And eventually, of course, that proton comes to this point, and that's where magnetic field ends, right? So magnetic field only within this grayish area. But when it comes to the end, so it leaves the magnetic field area. And of course, now there wouldn't be any cyclotron motion because the particle must move perpendicular to the magnetic field in order to experience circular motion. But at that point, magnetic field will be zero. And of course, these protons are going to fly along a straight line because there wouldn't be any forces acting on those protons, right? So now protons fly fast after being accelerated so many times, right? And so now you can position over here your target, right? Whatever you want to examine, explore, and so on. So direct application of a cyclotron motion, and that is the the first accelerator. So next application. Actually, when I was undergrad student right, in the university in Ukraine, we had the accelerator like this, just behind the building, right, buried in the basically in the basement. So, why is not flipping? Yeah, my slide's not forward. So next application. cloud or bubble chamber, which is used a lot by researchers, engineers working with elementary particles. So how does it work? So there is a chamber container. You see this cylindrical container filled with what is called a supersaturated vapor of water. What's so special about that medium? So it has this condition. So if you disturb it slightly with something, right, any point of this vapor, a bubble will be created immediately, right? So if you shoot a particle through that medium, of course, a charged particle is going to disturb that medium and it will create a trace of bubbles. So particle flies, creating behind a trace of bubbles. And of course, bubbles we can see, right? And we can take a photograph of them or make a video, right? So you see on top, there's a camera to record those traces. Because particle by itself is too small, too fast, of course, we cannot see that. But bubbles, yeah, we can easily see them, right? And we can easily take pictures of them. But if you just send a particle through this medium, right, without applying anything else, you wouldn't be able to extract as much information as if you position this container with this vapor inside of the magnetic field. For simplicity, uniform magnetic field. You see, we have solenoid. So here, basically, bunch of loops, right, and there, right. So basically, let's position this container inside of a uniform, basically inside of a solenoid, inside of a uniform magnetic field. And you see this red vectors, red lines, magnetic field lines. So now, if particle enters, right, of course, it enters perpendicular to the magnetic field lines, and of course, it is going to experience cyclotron motion. They're going to move along circles, and using those circles, or having information about those circles, we can extract more information about those particles. We will see in a second, right? So positioning inside of the magnetic field will allow us to get more information about these particles. Right? So now, examples of, for example, in 1932, a positron was detected for the first time. It was Dirac predicted that it's possible for them to exist and so on. And then using this cloud chamber, positron was detected. Basically, a positron, it's an anti-electron. It has mass of an electron, basically it's an electron, but positively charged, with plus 1.6 times 10 to the power of minus 19 coulombs, right? So that's why it is called basically electron or positron. And you see that this barely visible trace, this. So that's the trace of a positron. It was detected using this cloud chamber. And you see, actually, you can ask, why did they use this lead plate? In order to increase the curvature of the trace. So you see here, positron flew too fast, and it's difficult to measure, for example, radius of this cyclotron motion. So, but after slowing down, so now you can see the curvature of the trace, and you can extract information about the radius and get some additional information about this positron, right? Another example, I found it somewhere in the internet, I don't remember. So what do we have here? At this point, there is an atom, sitting, waiting. And then here, a gamma photon, basically high energy piece of light, right? Interacts, so this gamma photon interacts with this atom. And as a result of this interaction, here's what happens. So electron with large speed is produced, and it just flies that way, right? So large speed, because you see the curvature is not that large, right? So it just means it has large speed. And also it creates an electron, what is called an electron-positron pair. So you see here we have a positron circling. Here we have an electron circling. Of course, you can ask, so how come? We discussed cyclotron motion, and in our motion, charged particles moved around the circle. But now we have this spiraling trajectory. but explanation is quite simple, right? Because we discussed in our discussions, particles flew in in vacuum, right? But here, these particles travel through this vapor, of course, colliding non-stop with these molecules of water, right? Of course, they're going to lose significant amount of energy, right? Slowing down. And of course, as particle as particle slows down, of course, cyclotron radius getting smaller and smaller and smaller, basically spiraling in. Right? So we will see trajectories like this. Okay, so now, of course, you can ask me, so how come that we can, how is it possible to tell that this particle is positively charged and this particle is negatively charged? We can easily extract this information by analyzing these circles, right? So of course, as an experimentalist, you know direction of your magnetic field because you designed this setup, right? So you know direction of your magnetic field, right? So let's assume magnetic field is into the screen. You see crosses, right? Then, of course, by looking at this trajectory, okay, this upper trajectory, of course, we know it's the direction of the particle. For example, at this point, of course, direction. Why it's not flipping? Yeah. So the direction is velocity is that. Just tangent to the trajectory. That's direction of the velocity. And now this is the formula for the magnetic force, right? And of course, this magnetic force is responsible for this circular motion, right? So we need to analyze this formula properly. Look, so what can you say about the direction of V cross B? We see direction of V, we see direction of B. Right hand rule number one. So align your hand along direction of V, right? And then orient it like this so that you can bend your fingers towards the vector B. As a result, V cross B is that way, right? That way. And that is also direction of the velocity, right? So you see direction of the velocity because since particle spirals like this, so it means velocity, I mean the force points that way. So you see direction of velocity, direction, wait, why I keep saying velocity? It's 8 a.m., right? Direction of the force, you see direction of the force and direction of V cross B exactly the same. It's possible when? It's possible only when charge is positive. If charge is positive, this direction and that direction must be the same. And that's what we observe for this particle. And that's why we can tell that, yes, this particle must be positively charged. And that's why I told you at the very beginning that it makes sense to position this chamber inside of the magnetic field because you see the circles and we can extract information about, for example, a charge of these particles. If we didn't position this in the magnetic field, we wouldn't be able to tell if this particle which just flew through the bubble chamber positively charged or negatively charged. But now we can extract additional pieces of information, right? Again, because the direction of V cross B that way is exactly the same as the direction of the force. Right. So that's why that particle must be positively charged. Now let's analyze in exactly the same way this particle. Right. So in exactly the same way, so of course I can tell immediately that this is a direction of the velocity, right? You see that? Tangent to the trajectory. And of course, since particle curls that way, so we can tell immediately that this is direction of the force because this force forces this particle circles like that, right? And so now let's look at the cross product of V cross B. So V, okay, probably I need to position myself like this, right? In order to get that done. So, no, still, I cannot. So V, right? Yeah, like this, V, along V. And then, yeah, my orientation of my hand is correct. So I can bend my fingers now, you see, in the direction of B. And you see my thumb gives me direction of V cross B. So V cross B that way, but the force F is in the opposite direction. So these two vectors are in the opposite direction. So it means that look at the formula now for the force, magnetic force. V cross B in one direction, but force is in the opposite direction. It's possible only when charge is negative. Right. You see, by analyzing directions of V cross B and F, we can tell immediately what's the sign of the charge. In this case, this is a negatively charged particle. Right. So that's how we can extract that information. Okay, so enough of that. And now a question. I think there will be a question for you. Yeah, question for you. And something like this I gave a few times among multiple choice questions on the exams. There will be some trajectories, and I would ask, so what's the sign of this charge or that charge? You just need to analyze this formula for the magnetic force, analyze directions. So it's not that complicated. You just need to do it a couple of times, and straightforward. So now the question for you. Now in the chat I created like 5 conceptual questions. So this is number 1. So keep track of numbers. So it's a conceptual test 1. So what do we have here? You see we have a uniform magnetic field into the screen pointing, bunch of courses. Then we have 2 particles with the same mass, and they fly in the same direction and enters magnetic field at the same point, this, and they have the same speed. But we don't know any information about the charge, their charges. But we also know that one particle is going to follow trajectory A, follows, and the second particle goes along trajectory B. Right. So we need to answer the question using this amount of information, which particle has the bigger charge. And there are also options C. Both charges are equal. So option A, this particle has a bigger charge, or B, this particle has bigger charge, or both charges are the same. And D is impossible to tell from what is given. Okay, give it a try. Right. And let me see your answers. This chat. Yeah. On purpose, I give the formula for the cyclotron radius, right? So let's analyze it piece by piece. Masses, they have the same masses. Then velocities, not velocities, speed. Their speeds the same. And also they enters, and they're exposed to exactly the same magnetic field. So this mv divided by b is exactly the same for both of these particles. So what can make radius different? Q, right? Q. So, and since charge Q is in the denominator, it means that the bigger charge is going to give us smaller radius, cyclotron radius. Let's see which trajectory has smaller radius. Of course, trajectory B. So it means that particle which follows trajectory B has bigger charge, right? And of course, particle A, okay, particle followed trajectory or following trajectory A has smaller charge. Right? So that's how we can analyze that. Oh, I need to bring slides forward again. So since yeah, okay, you can read it, what I just told you. Now, additional question. By looking at this picture, can you tell me about the sign of these charges? Are they positively particles? Are they positively charged or negatively charged? To answer this question, we need to run analysis similar to what we did in just previous slide. Right? We just need to look carefully at the formula for the magnetic force. We just need to look at the direction of V cross B and compare the direction with the direction of the force. Right? Direction of the force we can see since particles bend trajectory bends since trajectories bend this way, so it means that force is that way. Okay, this way. But v cross b, okay, velocity is up, right? So velocity is up, so I have to position my hand like this, and magnetic field is into the board, so I have to orient my hand like this. So v cross b, and it gives me this direction of the v cross b. So it's the same direction as the direction of the force. So direction of v cross b, the same as the direction of force. It means that both of these charges, both of these particles are positively charged. Both of these particles are positively charged. But if one trajectory, for example, were bent that way, it would mean that that particle would be negatively charged. Right? So that's how you can analyze and get the information about the charge, the sign of the charge of the particle. Again, many times I give a questions similar to this among multiple choice questions. So what's next? Okay, so enough about cyclotron motion for now. Now let me just, before I jump to the next chapter, next important section of this course, very important section, let's just digress a little bit and to the physico-philosophical level. Right? Okay, let's discuss quickly what is called Ørsted experiment. So I think it was beginning of 19th century. Yeah, 1819. Ørsted, Hans Ørsted. He was showing, again, according to the legend, according to the books, right? So he was showing some demonstration, right? I know, to people. All right, and in that demonstration, he had what? Just a long piece of wire connected to a battery, right? So he was driving a strong current through that wire. Actually, I can open it up. All right, so here, strong wire. And at that time, again, according to the legend, the compass was nearby. So there was a compass. And he noticed that whenever he turned on the current through the wire, compass responded. It sounds like, yeah, so what, right? So yeah, all right. But nevertheless, lots of people believe and thinks that this is probably one of the most important experiments ever done. Sounds so strange, right? So it's such a banal, for us, seems like a banal observation, and nevertheless, some people believe that that was one of the most important experiments. How come? What's so special about this? And what is so special about this? Back then, before this observation, people believed that there is an independent, okay, there was, let's say there is an independent world of electricity. It's basically the way I present you the material. So pretty much up to this point, we started first describing and learning the world of electricity. And we pretty much presented it as an independent world, right, with its own president, government, right, whatever, right? Just an independent world of electricity. And then there is an independent world of magnetism, again, with its own rulers, but two independent worlds. And back then, 250 years ago, so some researchers were digging up into the world of electricity. Some were playing into this playground of magnetism, right? So they were having fun there, some of them having fun over there. And they thought that these are two independent worlds. But what did he observe here? That electric current, pure representative from the world of electricity, compass needle, permanent magnet, it's a representative from the world of magnetism. And these two representatives from two different worlds, they interacted. So it was the first time when people realized that these two worlds are not that independent, that they are connected. How deep the connection? Of course, they didn't know, but they realized, damn it, these are connected worlds. And as a result, lots of people started seeing potentials, right? All right, in diving into this research. As a result, this demonstration encouraged, right, forced lots of brilliant minds to dive into this world, into the research of this world, right? So like Ampere, right, then later Faraday, then Maxwell, and so on and so forth, right? So this demonstration triggered tons of research because people realized that that this world is not as simple as they thought, right? Okay, so that's why this seems like a simple observation demonstration is considered as one of the most important experiments ever done. Because it encouraged bright minds to dive into this research.